to the second part to talk about some additional the information or some more message about this gradient ascent method. So one is about the initial value, and also we will talk about the step size and epsilon rows within this function. So that we can have a little more understanding of how to correctly use this function. So in the last video we create this generic gradient, the ascent, and we gave let me close this one. So it should not have that. And the initial value of a variable for which we start the iteration of the gradient ascent play a very important role in this algorithm. So consider this function. So let's try to run this again. So this second. So let's close this first. So we run this second one and ask for our function. So we give this x powered by 5 and 30 times x powered by 3 and 5 times x. That is our function, and we put the variable is x. So we know that is the there is a curve. So if we see the value is the minus 2, so it will get this ascent. So they will go to this direction, because if they move to the more positive, it will be descent. So it will go to the left part, because it's on this curve to go to the increase. So that in this example is if you start from the minus 2, it stops at the peak that also corresponding this global maximum. But let's consider, so if we give this to this 0.5, what will be happen? So I still have this 5 minus 30 times x times powered by 3 plus 50 times x, and the x now is we use this 0.5. Why we cannot get this 705 as the maximum range, but we got this 25? It's because if we see the 0.5 is around here, and here is if they want to go to the left, it will be decrease. So it's only the go to the right will be the increase. So that will be same if I put this positive 2. Let's also have that again. So let me see here. I just paste x is 2. So you can see it's also back to here. So the only thing is, so I will put in that is because it's even as I put here. So it will go to here, and if I put this more than, I think it's more than 5. Let's see. So what will be happen? Let's see. I have a 5. So 5 is already on this edge. Then looks like it's they have a long the calculation, but it's always go to the increase. So that means you don't have our a curve is getting that into the 0. So then this will not be stopped. But what we will have our idea is if you choose the different initial value, actually you may get the different result, and some result maybe is not the expected one. So using this method, the one important caution is try to choose or select the initial value carefully. Some variation of the algorithm try to address this limitation. So, but within us, we just need to ensure is that this initial value. First, you have to understand what the curve looks like. Then, choose this initial value properly. And the second is the role of this step size. So in this gradient ascent algorithm, the next value for the variable is calculated using this formula. So the theta new is decided by the theta old, and plus our very this step size times this the first order derivative value. We call this a step size. This size determines the distance of the next step. So the this side is every this point distance in this XL. So you can see here, if you choose this in the more and more smaller, it will ensure is you don't skip this one. But if you see is I choose this one and my step is quite big, like this big. So maybe next step is coming to this and we skip on this bigger one. So that is also may impact your the decision. But because we are using this derivative within the calculus, we should choose our step size as smaller as possible. But when you make that too small, it will occupy the calculation resources. So that is the balance side. So if the so that is we already have that. And another is that is epsilon that determine when we decide to stop the iteration. So it's epsilon is used to compare. So but if this compare is not smaller enough, then that's it's very easy to stop. Then that's also may not get this correct result. So we use this this -6 as the power of 10 as the epsilon for all the functions. So this value, although sufficient small and suitable for this function, but it may not be the right value for other functions. So it's a good idea to verify the maximum value at the end to ensure its correctness. So if needed, you can adjust this epsilon accordingly. So until now is if you keep using this function, so you should carefully select the initial value, carefully validate this step size here, and also this epsilon value. So that is the things. So step 2, the gradient ascent algorithm also implement that for the algorithm of to determine the equation of this one is the first order. This derivative must have a solution. So if we don't have a solution, then we should have some errors. So we can make this program more useful for such case by incorporating our check for whether this first order derivative has a solution. So now let's make our third one to have a little more enhanced. So we put this as the 3 enhanced. At checking for existence of a solution for the equation f(x) equal to 0. So let's see. So here we will do the trial solve. So we will need to load this the solve class. Let's say here what we can continue the keep. So for our gradient ascent part, we got this 3. Then first we will do the check. So check whether f(1x) equal to 0 has our solution. So what we can do is we will do it if not solve f(1x). So that means if our false, then we print cannot continue. Solution for this one equal to 0. That's not exist. And then with format as f1x. And then after that is we will directly return. So and then we see here all those are still keep, and all this one. So varies is keep, and here. I think it's this if. So we have also we will check if we got this max, because if that not solvable, then we will return our empty or return our the false. So we will need to put this here. Then we start is let's do our testing. So what means we don't have our solution is this log x. So log x is the like C. So log x. Oh, so let's run this. Oh, we have some error. So unexpected indent. So on which line? So line 1. So I think it's the saving issue. Let me put. Yeah. So sometimes you need to wait some more seconds to let Visual Studio to finish save. So log x. So x is our variable that gives this initial value 0.1. Okay, cannot continue. So that is the this one. So we can use this to do. Let's see what's the ex. So can I put that is the 0.1? Oh, cannot continue as well. So you can also test this too. So I hope is you can get this same result. So the reverse algorithm of the gradient ascent is the gradient descent, as I also mentioned. It can also help you to choose the global minimum. And it is similar to gradient ascent algorithm, but instead of climbing up, it's well climbing down. So if we challenge 2, we will discuss is the difference between these two algorithms, and then is we can implement that descent the algorithms. So see you in that challenge, and also we start is we finish this 7.6 subchapter. In next chapter, we will move to this integral, the parts, and that is the inverse, the operation for our current derivative. So see you in that video. Bye for now.